Okay. So I hope you guys had a nice coffee break, and I hope I left you with some questions, right? Like I ended up the lecture saying that by including topology change, we get new interesting phenomena just from the point of view of anomalies. So what more can we get of it, right? So this lecture is about what can you get from just assuming there's a strong form of topology change in quantum gravity, and what you get is, as Irene described on Monday, a lot of global symmetries which you need to kill, and that's related to the Cobordism conjecture. So that's going to be the topic of the lecture. But before I go on to do that, let me first try to describe a little bit why or to what extent do we believe there is topology change in quantum gravity. Why do we believe that in quantum gravity you need to do some topology? Well, first of all, one would say perhaps point number one, it's a natural idea. I mean, after all, in quantum gravity, the metric itself fluctuates, right? So the distance between 2 points fluctuates. So why not topology? And this is goes back to a very old idea of Wheeler, which he called the space-time foam. Is the idea that topology is fluctuating at the level of, if you go to very short length scales, there's like the topology of space-time is fluctuating. What that means is that if you look at a small box, at some point it might have like the topology of a ball, but the next time it could be a ball with a handle attached, and then you look again and it's a ball again. So it's quantum mechanics, so it fluctuates. Okay. So this is a very old idea. It comes out very naturally, but what is the evidence that we have for it? Well, I would say we have evidence for it coming from string theory and holography. So the first line of evidence coming from string theory is that string theory we understand very well, and in certain cases we know it behaves in a very smooth way under topology change. So so just to be more concrete, you can consider compactifications of string theory. The standard thing that people have studied for ages. For instance, you could consider type 2 strings on Calabi-Yau threefold. What that means, you have the 10-dimensional string theory. You compactify on a complex 3-dimensional Calabi-Yau manifold, and this Calabi-Yau manifold has moduli that control its shapes and its volumes and whatever. And this moduli in the string theory, they are related to fields. Okay, and if you have just a Calabi-Yau threefold, they have a lot of supersymmetry. So actually, these fields, they don't have a potential. So what that means is that you can choose the vacuum expectation value of this field however you like, right? There's a modulus. But at the same time, they're related to the moduli of the Calabi-Yau threefold. And there's some moduli change the topology of the Calabi-Yau. So in particular, when you can get close to what we call the conifold point, so conifold points, you can tune these fields, you can tune the web of these fields, you can tune this moduli. This is something that you are completely allowed to do because it's protected by supersymmetry. You can just tune the values so that you develop locally a singularity of the form. For instance, you can parameterize in a number of ways. Okay, so you can have locally singularity like this. And this singularity looks like a cone over S3 times S2. It's a singular space. It's a singular space. But string theory does not care. Does not care. It's completely smooth, and you can deform it in two ways. You can deform it in a way that you make the S2 have finite value and the S3 remains at zero size, or you can deform it in the other way. So that the S3 has finite size and the S2 has zero size. These two guys have different topology. And so if you were doing general relativity in here, it would be a mess, it would be difficult. But if you're doing a string theory, everything is completely fine, it's completely smooth. So string theory is certainly telling us it's okay to have topology change. It is not telling us that topology change is necessary. So to give you an example where, and also, you know, this is all very supersymmetric, blah, 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 blah. There's another line of argument that tells you that you need to have topology change, which is holography.
Sorry, Miguel, before you proceed.
Yeah.
So would you agree that the handle on the D3 brane is more dramatic than this topology change for the field theory?
What do you mean is more dramatic?
Because it's not a continuous process. It's like, it looks like a soliton in the gauge theory or volume. Sorry, the gauge theory of the D3 brane. This handle thing.
Oh yeah. So from the point of view of from the point of view of the volume gauge theory, you're actually changing the manifold. You're by hand changing the topology of the manifold where the D3 brane is in. It's not like here, because in here you're actually it's described in terms of dynamical fields, and that doesn't happen in the case of the D3 brane. That's what you mean, right, Fernando?
Yeah, it looks like the position fields for the D3 brane that you can think as fields in the gauge theory and so on. They have some solitonic profile, something weird, which is this handle. I mean, I don't know.
Yeah. That's right. That's what it is.
That is,
also like
that is the thing. This is a continuous thing.
Yes. So this is right. So this is a case where you can describe it in terms of just giving a wave to some field in the compact theory. But honestly, for instance, if you were to compactify n equals 4 Superia Mills, let's say on a 3-sphere, and you would grow handles on this 3-sphere, you would also see it a bit like this. Okay, so the reason why it seems simpler here is because you've compactified internal space, right? I agree with you. This is much better controlled because this is supersymmetric, and growing a handle, it's certainly not supersymmetric.
This change of topology that you presented is simply that in one case S3 is contractile and S2 is not contractile, and the other case is S2 that's it, no?
That's it.
Essentially the flash, in one case you put a non-contractible sphere and something that is contractible. This means this non-contractible need to have some topological defect inside, and you change the role S2 on S3 in this sense, right?
That's exactly right. That's exactly right. So, I mean, this is the usual conical transition from the 90s, right? Like this is yeah, that's all there is. But it does change topological numbers like H11 of the Calabi-Yau. They do change because of this process. So it's genuine topology change. So the second example that I wanted to present, which I think to me is very, very convincing and very nice, because it's also non-supersymmetric and so on, is holography. So what is holography in ADS-CFT correspondence? So very briefly, the ADS-CFT correspondence allows you to relate a quantum theory of gravity in a space of negative cosmological constant, ADS, to a conformal field theory. And the precise statement is that the partition function of the conformal field theory, you know, in some manifold or whatever, some background fields that I don't want to be precise right now because this is not a course about holography, is dual to the partition function of ADS. And furthermore, the partition function of ADS in semiclassical gravity at the semiclassical level, so this is an approximation, it's semiclassical, it's a sum of the Euclidean action of different saddles, okay? And then one saddle can dominate versus the other and so on and so forth, okay? Now the CFTs that you get in ADS-CFT, the holographic CFTs are often theories with a lot of degrees of freedom, with order, but on some parameter n, we have n squared degrees of freedom. So these things are typically gauge theories with SUN gauge group, and they have SON, they have order n squared degrees of freedom because the adjoint of the gauge group of SUN is, you know, quadratic in n. So this theory is with order n squared degrees of freedom, and they confine at low temperatures. and deconfine at high. So what that means is when you compute this partition function from the CFT point of view, there are some more than one coefficients that you cannot determine, but just from this structure, you know that the partition function is gonna go like e to some order one number at low temperatures, and it's gonna be mostly insensitive to T, and then it's gonna get a very big like dependence, which goes like n squared T squared at high T. Okay, so what that means is that this is the confined phase, and then the free energy, which goes like n squared in the deconfined phase. Physically, this is very intuitive. You just have a box with the CFT, you heat it up, and once you heat it up, you start seeing all the degrees of freedom, but only once you heat it up enough. Okay, so the way you see this double structure that you have in the CFT, you expect from general points of view. In the bulk, is you see because when you compute the right partition function in the bulk, you need to sum over two saddles, which are empty. So you need to sum over the action of empty ADS and e to the action of what is called a Schwarzschild black hole. And these are Euclidean saddles. So these are actually saddles with different topology. This has a topology, for instance, of something like S3 times disk. Okay. And sorry, no, it's the other way around. Sorry, this one. Sorry. This one has a topology like. Yeah, so it's the topology of a ball, like it's a circle, and this was the kind of topology as S3 times the disk. So there's two saddles with different topologies. They dominate at different temperatures, and this one has dominates at high temperature, and this one dominates at low temperature. The basic point I want to emphasize is that agreement with field theory requires you to sum over all topologies. If you write down all the topologies, in this case, you also need to worry about boundary conditions and so forth, but you write down all the topologies that matter, you typically get agreement. Agreement with field theory requires sum over topologies. And this thing has been taken to the next level by the recent literature. So there's some counting of black hole microstates that you can do in the field theory and also in the bulk dual. In the bulk dual, you need to sum over a bunch of saddles. Sometimes even singular saddles, which must have the right topology. But the basic idea is if you include every saddle, every possible topology, then you get agreement with the field theory. Okay. So I would say that also holography provides us a very strong motivation that topology can indeed fluctuate in quantum gravity. We need that in holography for it to work. Okay, so those are two very good motivations that we believe this topology changes in quantum gravity. Okay, any questions about this?
Sorry, Miguel, so probably it's a very stupid question, but what do you mean with confinement exactly?
So right. So what I mean is that right. I mean like in QCD, right? Like at low temperatures, the fundamental degrees of freedom of the theory, which are like these gauge bosons, they don't translate themselves into physical degrees of freedom. Just like in QCD, you have the quarks, but at very low energies, the basic excitations that are around the vacuum are things like pions. Okay. So something like that happens in equals for super-Young Mills, for instance. Okay, so the physical states that you have in a box are they're dual, not so much to the fundamental gauge fields, but to things like single trace operators and the like. Okay, now as you increase the temperature, at some point so the basic point is that the gluons they attract each other and they become bound, and if you increase the temperature to a high enough value, then the gluons become deconfined and you start seeing all of them. So in these theories, what happens is that at very low temperatures, you're supposed to see not too many degrees of freedom, and at high temperatures, you're supposed to see a lot of degrees of freedom. So the confinement in any quadratic parameter is not exactly the same as I described as in QCD, but the behavior of the free energy is what you would expect. And if you want these two things to match, you need to do some more topology in the bulk. Did I answer your question, Edu?
Yes, thanks.
There's a very nice paper by Witten on all of this, which is called Antidescending Space and Confinement. Anyway,
Miguel,
yeah.
can you develop a bit your last sentence? So agreement with field theory requires some over topology. What do you mean by that?
Well, so what I mean is that if you have, so from general free theory arguments, you expect that the free energy goes like some number, doesn't depend strongly on T at low temperatures, and at high temperatures depends like this with some number that goes like n squared. Okay. For you to recover this result from field theory side, from the bulk point of view, you need to do this sum over saddles of the gravitational path integral. And then if you just compute, for instance, the saddle, MTADS saddle, it will give you this behavior at all temperatures. It will not give you that behavior. If you include this other one, it will give you this behavior at all temperatures. It will give you this other behavior. It won't give you the first one. When you include the two of them, then there's some regime of temperatures where the first saddle dominates, and at some point there's a transition to the other, and you get basically a step function going between one and the other. So to reproduce the structure from the bulk point of view, that's what I mean. You need the sum over topologies. Okay. Did I answer the question?
Yes.
Okay. Very good. So agreement with field theory requires the sum over topology. So fine. I'm just gonna, I'm just gonna take this to be a thing that I can do. And so if I can, what can I do if I can sum over topologies? Well, I can certainly do the following thing. I'm just gonna just for concreteness, we could do this in more dimensions or whatever, but just for concreteness, imagine we have a 5-dimensional theory of gravity. So this is the T equals 0 surface. So there's an R4. And since I can sum over topologies and I can change topology, I'm gonna glue a K3 here. I mean, why not, right? I can certainly glue a K3. There's nothing wrong with that. And as we've learned from Maroon's lectures and also Weber's lectures, he was telling us about the Pontryagin class and how it's a Cobordism invariant and so on and so forth. We know that there's a number that counts. If I put NK3s, for instance, there's a quantity which is the integral of P1, which is basically the number of K3 particles that I glued. Okay. So you probably see what I'm going. This looks, there's a charge here, and once I put these guys here, there's no way I can change this number. This number is topological invariant. So you can the guys can collide or whatever, but in principle, you don't expect that this number can change. And so what I want to say is that by adding K3s, I've got an equal surface charge, which looks a priori, if I don't think harder about it, looks like a global symmetry. Okay, but wait, there is something that I need to take care of. I say that there is, I'm saying that gluing K3s like this might be a global symmetry. And I'm doing this because I allow for topology change. But topology change can also kill some topologies. So
Miguel, can you say something about in which theory are you now? You started with R4, means you are in a gravitational theory, on some field theory. What is the picture?
Yes. Sorry. Yes, that's correct. I'm talking just for concreteness. Okay, this is more general, but for concreteness, I'm going in a 5D theory of gravity. Okay. I'm doing 5D simply because then this K3 is a particle. If I was doing it in 10D, it would be more like a brain. It doesn't matter. But just for concreteness and to connect with the usual story, I'm just going to say it's a particle. Okay. Sounds good?
Yep.
Okay. So there's this 5D theory of gravity that I have here. And I look at the T equals 0 slice and I'm gluing the K.
Oh, what is P1?
And I want to say this is a conservative. Yeah.
What is P1?
Sorry, was there a question?
You calculate integral of P1 of the number of K. Okay.
Okay. So so I have this thing, and then there's the and so I want to say that by
Miguel, you are working in 5 dimension Euclidean or Minkowski, or you cannot care less about that.
So in the end, I'm not gonna care. But if you want to be very concrete, I think with the first example is very good to be concrete. Let's say I'm working in Minkowski signature, okay?
Minkowski.
But it's not gonna matter in the end. Cesar. Yeah. If you want, this is just I want to make it very physical for the first example. Then it becomes more abstract, and then the distinction can become important. But for the first example, I want to be very concrete. Okay? Yes. Good. So this is the 5D theory of gravity, and I want to say that there's a global charge because there's topology change. But I have to be a bit careful with that because topology change, you know, can give you things that look like a global charge, but it can also kill something. So for instance, if in a theory, if I don't allow for topology change or for arbitrary topology change, for instance, if I have a handle, which I'm drawing with my beautiful drawing skills. So if I have a handle, right, that looks like a conserved charge, like you know, the number of handles on a Riemann surface is famously conserved. But if I allow for topology change, I can certainly do something like, you know, I pinch the handle here, something like that, and then, you know, it just disappears. So topology change can give you some conserved charges, but it can also kill them. So the charges that survive, the conserved charges that survive are the ones that cannot be killed by topology change. Well, and now here comes the main point that you were all waiting for, which is Cobordisms. What is the most general description of topology change in quantum gravity? Well, I'm just going to draw my initial guy. This is the picture you've seen a lot of times in this lecture now. I'm just going to draw some manifold M. I was making it non-compact here. You could make it non-compact or compact, it doesn't really matter. You could always, one thing that we like to do in physics when we have a non-compact R4 is we compactify this to an S4, and then this just becomes K3. So you have some manifold M, and you have some other manifold M prime, to which you get by some topology chain transition. And I'm gonna draw the topology chain transition as a movie where, you know, some fictitious time parameter goes to the right. Okay, and then, you know, things can happen here. They can be splitting and joining or whatever. So the basic description of topology change is a Cobordism. Between M and M prime. And so, what it follows is that global symmetries from topology change arise from Cobordism invariance. And what is the strongest Cobordism invariant? Well, the Cobordism group itself. So in particular, if you have a Cobordism group, let me just double check so that I get this exactly straight for you. So if you have a Cobordism group of degree P, you can glue objects the way I described it. So you end up having what we call in the language that we're going to use on Monday, and D minus P minus 1 form global symmetry. Okay. So voila, with topology change, we get global symmetries. Any questions so far?
Yeah, why global symmetries arise from topology change? I don't. So I'm struggling to understand that thing.
They are not killed by the topology change.
Yeah, but what
Sorry,
I mean, so far we were talking about anomalies, and now these global symmetries appeared again. But how do they appear in this picture?
Sorry. I guess I was not very clear. So the content of the lectures is what things is Cobordism theory useful for in physics. So in the previous lecture, I described anomalies of some symmetries, and now we're changing gears. Okay, so now we are in the previous lecture, Cobordism was important because you would take the topology change allowed for more general paths in the configuration space of connections, which allowed for more general anomalies. Now we are forgetting about anomalies, and we are just considering the fact that because we have topology change, we can add objects with non-trivial topology. You can just glue them to flat spaces. So it's a different point of view. There's no obstruction in you, for instance, gluing a K3 to R4. Okay.
My question is, how do global symmetries appear from this topology? What is the relationship between this topology change and the global symmetries? That I don't know. This was not explained.
Well, right. No, so sorry. So there's if you, for instance, if you have this K3 kind of thing, the P1 is you could say it's a conserved current, okay? Because so in the language that I was showing before, okay, this equation is true because the first pointer in class is closed. So this is exactly the equation, the condition of having a global current. So it's the condition of having a global symmetry. Okay. So that's where that's how the global symmetry arises. And this description it connects with the global symmetry, with the usual global symmetry description, but it doesn't tell me if the symmetry could be violated by processes that change topology. Okay. So I could imagine that if I'm compactifying the K3, then the topology could change, and maybe that gets rid of this charge. But it can be the case because the K3 is non-trivial in Cobordism. The most general topology changing process is a Cobordism. Okay, so in quantum gravity. So charges that cannot be destroyed by Cobordisms are exact symmetries of quantum gravity. Look like global symmetries of the theory. Is it more clear now?
Yeah, but is it true that whenever I have topology, there is some associated global symmetry, or maybe some? I mean, that's you are saying that because I have some non-vanishing first contact class, then I can construct this global symmetry. Is this always the case that whenever I have topology, I can always do this thing? Or
well, whenever you have topology and a non-trivial Cobordism group, yes. Yeah. Okay. So there's a global symmetry. And Irene told us on Monday that there's no global symmetry in quantum gravity. So how do we fix this? Well, this is the basic idea of the Cobordism conjecture. So there's the Cobordism conjecture. Of McNamara and Baffa. Which is the idea that, these Cobordism groups that we are describing here, they are Cobordism groups in, with a certain structure, supergravity or whatever. The idea of the Cobordism conjecture is that actually these Cobordism groups are not the real Cobordism groups that you must take into account in quantum gravity. You must change the structure somehow, and there's some fundamental Cobordism group of quantum gravity, and the Cobordism groups of quantum gravity are actually all vanishing, which means there's no global symmetries. Now, what does this mean? Okay, what does this mean in practice? How do we define these Cobordism groups of quantum gravity? What do we mean? Well, to illustrate this, let me keep talking about the example of K3. Okay, K3. So K3 is the Cobordism class of K3 is the generator of omega-4 spin, which is C. Okay, so you cannot you cannot get rid of the so that's non-trivial charge. So what that means is that you have a K3. You cannot. This thing is impossible. There's no way to write K3 as the boundary of some 5-dimensional manifold. Okay, which is smooth, has a metric, and so on and so forth. All the nice things that we want. But in quantum gravity, we can allow for singular configurations. Things that are not manifolds. I already gave you an example before when I described the conifold here. So when I describe the conifold, this thing is smooth. This thing is smooth. But the transition point is that it's not a manifold, it has a singularity. String theory is okay, manifolds with singularities. And so even though it's impossible to find a smooth manifold such as that K3 is a boundary, it might be possible to find something like some singular object such that K3 is a boundary. Then the Cobordism conjecture, what it's telling you is that these kind of objects, which are singular geometries from the bottom-up point of view, you wouldn't know if you have any right to include them in the gravitational path integral, have to be included. Okay, so that's what the Cobordism conjecture is telling you that you should be able to do. So you must always include this this singular object in the gravitational path integral. And these objects allow you to kill the Cobordism tests. There's another way to describe the same, which is compactifying on K3. Okay, so before I was drawing the K3 as some object that I add on R4. But in string theory, we also like to compactify on this manifold. So you can compactify for instance, the 5-dimensional theory on K3, and so once you compactify on K3, so you have the K3, and then there's some non-compact direction that is left over. The fact that you have a defect like this, that you have a cobordism, means that you can write down a geometry like this, where the compact space shrinks to a point and ends. Just to give you a more familiar example, which is easier to picture in your head, imagine you have a Kaluza-Klein compactification, so a compactification on a circle, and then you write a geometry where the circle is the boundary of a cigar. If you have some direction in the one of the non-compact directions here is R, and this is the size of the Kaluza-Klein circle. The Kaluza-Klein circle shrinks to 0 size at a finite distance, and after this there's nothing. Okay, this kind of configuration in string theory we call a bubble of nothing. And so Cobordism conjecture, another way of stating what it tells you, is that means that every string compactification admits a bubble of nothing, at least topologically.
Another question.
What do I mean by topologically? Well, what I mean is that once one wants to do something like this in a string compactification, one needs to also solve the equations of motion and find that right metric and all of that. I'm not doing any of that. I'm just describing what can happen topologically. And what the Cobordism conjecture means is that there's no topological obstruction to the existence of bubbles of nothing. And this is very far-reaching implications. For instance, if this thing is true, it means that there's you can find a boundary condition for the standard model, an end of the world brane for the standard model. And for instance, you can then study the degrees of freedom that live there and so on and so forth. It's a very interesting kind of story. So now I'm gonna describe. Yeah, okay.
Question. So given any manifold, it's the boundary of a cone over that manifold, right?
Yes.
So why is this a conjecture? Like it's like obviously true.
that is an excellent question. Okay. So the point is that, right, so from topological point of view, right, if you're a mathematician, you just topology, this is like what you just said is true. The point is that the cone over some manifold very often has a singularity that cannot be smoothed out, doesn't have a smooth geometry. Okay. So it's not obvious from the point of view of someone who is doing supergravity that you are actually allowed to include the cone over a manifold as part of the configurations in your theory. Okay, so in physics, we typically do things like general relativity, and that's a theory of a typically it's a theory of a manifold with a smooth metric. Okay, now we know that in string theory we also allow for certain kinds of singular metrics, but we don't certainly have a general classification of which singularities are allowed and which ones are not. Okay. And so what the Cobordism conjecture is telling you is which kind of singularities are allowed. For instance, I know because of Cobordism that the cone over K3, it's okay. Okay?
But can you say clearly which kind of singularities, topological singularities you admit?
I don't think
a class of links of the singular points.
I'm not sure I can say that. I can say that in general. So the Cobordism conjecture only tells me that there has to be something, so that such that I can put, so that I can put something like this. But it doesn't really tell me what exactly is the structure or topology of things that I can put here. From far away, it's gonna look like the link of the base of the cone, yes, but locally that probably depends on microphysics, depends on one string theory or the other. So I don't think I can give you a general answer. Cobordism conjecture only tells me there's some answer to that.
Because I meant that
let me perhaps.
There was a construction of bus that when you list a sequence of links that you allow, then you can modify Cobordism ring just mod out by this by this sequence.
Oh, I see. I'm not familiar with this, but sounds very interesting. I'd love to get a reference for this.
So it's 70s, I think.
It's 70s. Okay, I'm still not familiar with it. And if you could send me the reference, that would be awesome.
Yeah, it's related to Andrei's question. So does this conjecture tell us that we expect some boundaries with some prescribed geometry whenever you have a background, or is it telling us that we need to change our definition of the Cobordism groups in the way
that's exactly the latter? That's what it's telling you. So you need to change the definition of Cobordism groups to include this kind of defects somehow. Okay. So let me give you one example. Let me give you one concrete example, which I think is going to be very clear. Okay. So let me show you how this happens. For instance, for K3 again, I'm talking all the time about K3 in type 2A string theory. Okay, so in principle, if I look at type 2A string theory, it's a theory with fermions, and my first guess is that the relevant Cobordism groups are omega spin Cobordism groups, right? But actually, it's a bit more complicated than that. So what I have actually in type 2A string theory, so type 2A string theory is it's the same as M theory on S1. So what that means is that if I have the class of some manifold M in type 2A, on M theory is the class of M times the circle. Okay. So if I, for instance, have K3 on type 2A, on the M theory description, I actually describe it as K3 times the circle. Now K3 in omega 4 spin is non-zero, but omega 5 spin, which is the relevant Cobordism group, actually vanishes. Okay. So whenever you look, so what this is telling you is that from the point of view of M theory, the K3 compactification is never K3 by itself. It's always K3 times a circle, and it always has a boundary in spin Cobordism. So that means there's always, when you write K3 times a circle, there is a smooth way to write it as a boundary. When you look at it from type 2A point of view, where you make the circle very, very small, you have a K3, and it looks, basically, I'm just saying that there's a circle vibration over K3, okay? And when you project on the base, the projection of this thing on the base becomes very singular here. So from type 2A, it looks very singular, but not from the point of view of M theory. So in M theory, what you learn is that the Cobordism groups in type 2A string theory, the Cobordism groups you should be looking at are not just spin Cobordism groups, or something like spin Cobordism of manifolds which have a circle vibration. Okay, and the circle vibration can shrink at some point. And so that changes the Cobordism group. So what you learn from this argument in this particular case is that you need to change the Cobordism groups. And in this case, this was a simple case where you can describe everything geometrically, but very often the Cobordism groups are much more singular than this. Okay, the Cobordism groups that you get from quantum gravity. So for instance, let me give you another example. For instance, one thing that you can do in type 2B string theory, you can compactify, you can have a background which is an S5. Five sphere is constructible, but this sphere is threaded by some what we call F5 flux. So there's some flux. So there's some 5 form in type 2B string theory that which you know threads this thing and basically that means that the S5 is no longer contractible. Now, so if I draw the S5 here, this is the S5 as the boundary of a ball, I can contract it if I introduce some defect here, which acts as a delta for F5. So that the F5 is actually a delta at the origin. Okay. So Cobordism conjecture is telling you you need to add some of these objects. And unlike in the previous case, this is not something you describe with geometry. This is what we call, this is in this particular case, it's a D3 brane. So the Cobordism conjecture is predicting additional stringy objects that you were not predicting before. So I hope this clarified this a little bit. Was that the case?
So is S5 here is the internal manifold? I didn't. What is S5?
Sorry?
Is S5 the internal manifold?
S5 is the internal manifold. So I was changing now K3 by S5 with integral of F5 equals to N.
And what is F5?
F5 is a 5 form. Type 2B string theory has in the same way that you can have a gauge field, you know, and it has a 2 form field strength. Type 2B string theory has P form potentials for any P, and in particular has potentials for P equals 4. So these have a 5 form field strength, and you can integrate in a 5 manifold. And in the same way that when you write, you know, a gauge field, and things like the integral of F are Cobordism invariants of this group. Okay. So this class is measured by this. Then similarly, when you write of B, it has to be this should actually be B4 E1. That's the relevant Cobordism group. There's a factor of Z which is measured by this thing. Okay.
So the non-trivial content of the conjecture is that there are obstructions to existence of solutions in M theory / string theory, which are given by a suitable modification of the Cobordism group.
That's exactly right. What this is telling you is you can always introduce these modifications such that you end up. So and let me explain how because this is supposed to be like an iterative process. To describe how this is an iterative process, I need to tell you about the other possibility. So what these Cobordism defects are doing, they are breaking the symmetry. Okay, but Irene told you on Monday that if you have a global symmetry, it can be broken, which is what I just described, or also gauge. Okay, so what does I haven't explained to you what gauge means for Cobordism conjecture. What gauge means is that, okay, so when it's broken, for instance, you have a K3, then a compactification of K3 has an end of the world brane, so the universe ends. So there's a bubble of nothing. In the gauge case, what it means is that you are not allowed, you remove the class of K3 as an allowed background. And this is, for instance, what happens in hydraulic string theory. So let me describe what happens in hydraulic string theory. heterotic. I gave you an example where the K3s, the global symmetry to K3 is broken. That was M theory. And I'm going to give you an example where it's gauge, heterotic string theory. Heterotic string theory has a two-form field, which has what we call a Bianchi identity, which takes this form. So for simplicity, so let me just write it in mathematical language. Okay, so actually there's factors of 4 here. So anyway, so there's some gauge bundle which I'm gonna forget. So this thing I'm just gonna I was just writing for completeness, and I would forget about it. And say forget about this. And so heterotic string theory has a Bianchi identity like this. What does this mean? Well, what that means is that you cannot just compactify string theory on K3, heterotic string theory just on K3, because if you compactify on K3 and you compute the integral of P1, that's actually 48 or minus 48, I forget. But according to the equation above, this should be the same as the integral of minus 2 dh. But this is a compact manifold, and by Stokes' theorem, it has to be 0. And this thing is false. 48 is certainly not 0. So what that means is that you're not allowed to compactify heterotic string theory on K3. You can, of course, compactify heterotic on K3 if you turn on this other piece we forgot, or if you add NS5 branes. But from the point of view of Cobordism conjecture, the fact that the symmetry is gauged means there's a Gauss's law, means that you cannot compactify on such a background. And so the basic picture of the Cobordism conjecture is that there's a constant improvement, a constant process of improvement. You start with some Cobordism groups that you maybe read off in a naive way from your supergravity Lagrangian. You say, oh, there's fermions, so I'm going to put spin. Oh, there's some gauge fields, I'm going to put BU1 here, so on and so forth. Some natural thing you start with, and then you read off, you compute these Cobordism groups, you read what are the global symmetries, and then you add defects. Now, Cobordism conjecture in itself doesn't tell you which possibilities, in this case it's gauged, it's broken, but sometimes you get lucky and you can be more precise. So you add some defects. Once you add some defects, these defects often do at the same time break some symmetries, and they gauge some. Okay, and they produce an improved Cobordism group because they also you are now allowed to consider compactifications with defects. So it's the Cobordism group of original theory plus defects. And once you're here, you repeat the game. You would compute the Cobordism groups of this thing, which perhaps becomes very complicated because you're adding now singular objects that are not part of the supergravity description. But in principle, you would keep doing this. So you break against symmetries and gauge some symmetries. And eventually, after some steps, typically after a finite number of steps, you would reach omega equals 0. And that's the actual answer of quantum gravity. So the nice thing about the Cobordism conjecture is not the statement that you have no global symmetries, is that it tells you a way to try and, you can learn iteratively by following this process. Maybe you just do the first step. You already learned something about the theory. You learn some new defects that are there. And if you can keep it all the way, then it's great. Okay. I should mention that often when you add an object, at the same time, it breaks a symmetry and gauge 1. So these objects look a lot like, in a sense, they look like differentials in a spectral sequence. The way Arun was writing a spectral sequence, right? You have some entry here and some entry here. And if there's a non-zero differential, okay, then both of these classes, both these classes kind of disappear. And from the point of view of Cobordism, this differential is kind of like some object. This is a class which is broken, and this is a class which is gauged. And so this is just, I'm just making it's just a formal analogy. but it certainly looks like this process of iterating the construction of cobordism groups feels a lot like solving a spectral sequence to find the cobordism groups of quantum gravity. And in the same way that finding differentials is horrible, difficult part in a spectral sequence, also finding exactly which defects you need to add, it's very difficult in general. But you know, there are. I'm gonna be finishing the lecture today. So tomorrow I think I'll start the lecture by telling you a concrete, very nice application of the Cobordism conjecture, which we've used recently to learn about theories of supergravity in 10 dimensions, in 10, 9, and 8 dimensions, where we have actually learned something new that we didn't know before about string theory from this point of view. But sorry. Today, let me just finish by giving you some examples of Cobordism defects, and that both examples are where the Cobordism conjecture predicts known objects in string theory and some unknown ones. So some examples.
By the way, so would you say that there's an analogy with renormalization in that these are like adding counter terms, and basically the Cobordism conjecture says that okay, string theory and M theory are renormalizable in that you only need to add finitely many counter terms?
I see what you're saying. There's an analogy like that. Certainly, I never thought of it like that because many of these things are very, very difficult to describe from a Lagrangian point of view. So you could say, okay, fine, maybe I am, for instance, for some cases, you can say, well, I'm adding a deep brain to the configuration, and that's something I can describe at the DVI action on the Lagrangian and so on and so forth. But for instance, when you're adding something like an orientifold or a spin defect or some other objects, it's not obvious to me how to describe it in Lagrangian terms, but I do see what you mean. It's certainly telling you that after a finite number of steps, at least from this point of view, you reach omega of quantum gravity is 0. It's not saying, certainly not saying that gravity is renormalizable in the standard way, because certainly it's not. But there's some analogy there, yeah. And any more questions, please?
Miguel, can we come back to your analogy with the spectral sequences?
Yeah.
Just to understand the difference between gauge and so can we say that if some symmetry is gauged, then the corresponding class, say, falls, I mean, it's not anymore, I don't know how to say, but the representative is not anymore closed under some higher differential, whereas
that's right.
broken means is now exact under some higher differential. Can we say that? So I have in mind.
It's the other way around.
It's the other way around.
When it's gauged, is exact, right? So okay, so what I mean is that suppose I have a okay. So I think that the best way to describe this, I mean, it's really like more like I'm saying like spectral sequence, but it's more like just chain complex. So what happens is that when you have some quantum theory of gravity, okay, so some background, some background here, that let's say that the symmetry is broken, okay. So you can, so there's something that ends here, right? The theory of the boundary itself, you cannot compactify on that because it's charged under something else. You see what I mean?
Yeah.
The theory of the boundary itself it only makes sense attached to some bulk, so you cannot compactify on this thing. Okay. So at the same time, there's a Gauss's law for the thing of the boundary. It means that the thing on the bulk is broken.
Okay.
Maybe I think I wasn't clear. Maybe let me get back to you on this later.
Yeah, sure.
Yeah, I have one question. So maybe I'm not understanding this correctly, but from what you said, I understand that this Cobordism conjecture tells you that there should exist some construction of a Cobordism group which associated to M theory or string theory, which vanishes. And my question is, what does this tell us about the physics? I don't understand
Very good.
This seems like to be a mathematical question, right?
Excellent point. So this is something I didn't mention actually because of lack of time and because the useful thing for cobordism conjecture is really more the path means more than the destination. But certainly there is an independent way of defining the cobordism group of quantum gravity, and that's the physical interpretation you're talking about. So let me first define a cobordism group of quantum gravity. I'm gonna say that if there's a quantum gravity vacuum here, quantum gravity vacuum 1, and some other quantum gravity vacuum 2. If there is a finite tension domain wall between the two of them, so this is a finite tension domain wall.
I have no idea what this means.
So, okay.
Sorry.
Right. Okay, so
So you're trying to
So when
describe
you have-
a solution to the equation of motions that interpolate between two independent solutions, right?
Okay.
Yeah, it doesn't have to be a solution to the equation of motion. It just has to be some configuration that satisfies the Hamiltonian constraint, is a valid initial condition for GR. But it's just so in string theory, very often one has one particular compactification, okay, or one particular quantum theory of gravity and another one, and you can find configurations that interpolate between the two. Okay. So you can have two compactifications, okay, and then there can be solutions that smoothly interpolate between one and the other. Okay, so for instance, if you have a Calabi-Yau compactification and a different Calabi-Yau, you can certainly imagine interpolating from one to the other via a cobordism. So you have a configuration where you have compactification on Calabi-Yau 1 and compactification on Calabi-Yau 2, and the Calabi-Yau undergoes some cobordism here. And if you forget about, if you're just a low energy effective field theory observer that doesn't know about the internal topology, what you're gonna see is that here's some effective field theory, some fields, phi 1, phi 2. Here are some other fields, phi 1, phi 1 tilde, phi 2 tilde. And here, just as an experimentalist, you're just doing experiments. You're gonna see there's some region here where things are a mess. But once you go with your spaceship from here to here, here's gonna be a mess. But once you go through the mess, you're gonna find that you're in a different, in a sense, you could say you're in a different universe with different laws of physics, different fields. The ones from this Calabi-Yau and not the ones from this Calabi-Yau. Okay. Now, so far so good.
Okay.
Okay. So this picture that
just to see if I understand, you are changing the internal manifold from one locus of space-time to another. Is that?
This is what I did in this example to introduce the idea. But what I want to emphasize, what the cobordism conjecture is about, is that this part of it, the Calabi-Yau and all of it, okay, it's actually, So the Calabi-Yau and all of it is actually irrelevant. So the discussion that I said, what I meant by a domain wall between two quantum gravities, what I meant is that suppose you have any quantum theory of gravity, maybe it comes from compactification on some Calabi-Yau, maybe something else entirely, but you have some quantum gravity, by which I mean some effective field theory, some laws of the universe. And then there's another one. If there is any configuration like this, where you can cross, and after you cross it, you see the laws of the universe have changed, okay? Then I'm gonna say that quantum gravity 1 is cobordant to quantum gravity 2. This is just my definition. And it's a physical definition. I'm saying there's a domain wall that I can go through, I can pierce it, okay? I can send signals through. I can construct this configuration that allows me to go from quantum gravity 1 to quantum gravity 2, okay? If that is the thing, I say they are compatible. And then, so far so good? Yes?
Yeah, still I don't know what is a domain wall, so that's complicated.
Oh, right, domain wall, I just mean a region of space. So of course, if I have some fields here and the fields there are completely different, there has to be some transition region where things happen and it's a mess. I don't really know how to describe in the most general case how the fields on this side recombine to produce the fields on some other side. It can be very complicated in examples. But assuming that this is something that exists, and so here, physics here is very funky, okay? But assuming that I can do some basic things like transmitting energy through this thing. So this region is what I call the domain wall.
But
okay,
this, Miguel, this picture is in a space.
This picture is in space. This picture is in space.
Why I cannot think in time too?
You could think in time as well.
That's the reason I was asking you about the signature, because I can connect quantum gravity 1, quantum gravity 2 through space. I go through a region, blah, 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 my domain wall or whatever. But also I can think, okay, I can move in time and I can go from quantum gravity 1 to quantum gravity 2, moving in time, like an initial.
That's right. That's right.
In that case, the signature is important. This is what I was asking, if in order to define this quantum gravity cobordism, you are going to introduce an equivalence, like saying these are cobordant in my quantum gravity, only at the level of space transition, or also at the level of time, and in particular Euclidean time transition.
So I understand what you mean, Cesar. And this is I was careful to do it in space, because then I know exactly what I need to ask. What I need to ask for this thing is not even that it's a solution of the equation of motion, it's just that it satisfies the Hamiltonian constraint and momentum constraints.
Okay.
Because then it's a valid initial condition for GR. In the time process that you're describing, okay, then you know, I could certainly write down a trajectory like that. I can certainly just write down professor fields that do that, but it's not going to be a solution of, in general, it's not going to be a solution of equations of motion. So I'm not sure what is the physical interpretation for it. Okay, so I cannot give you such a
it's interesting, but then your definition of this quantum gravity cobordism distinguish very much between space and time.
The definition I'm using certainly does. My guess is that once one does it properly and in the full setup, it's not going to matter that much. But the way I'm defining, absolutely.
Mm-hmm. Okay, go ahead.
So Mari, I think it's Mari who was asking. Is that right? Before?
Yeah, it's fine. You can continue.
Yeah, but did you solve the previous question, or are we?
Yeah.
Are we going forward or backwards? I mean, I don't know.
I'm asking if we solved Mari's question.
I'm asking, yes, if the previous question was addressed or not. Mario,
it's fine.
I think you give up.
So maybe we can talk about it later, but I just mean that.
So I think what you were trying to say is the physical meaning of the cobordism question is this interpolation between two different theories. No?
That's right.
That's the message. Which is
that's right.
What I was saying the first day too. Like that's the physical meaning, that you can take theory, effective field theory 1, effective field theory 2. There should be some transition between the others. That's what the conjecture of no global symmetries is hinting to you. So there should be always some way of transitioning between 1 and 2, no? Call it domain wall, call it Hamiltonian something, like call it whatever you want to. But
the important thing is that it's a physical thing that you can transmit energy through.
But in the end, the Cobordism group has to be vanishing completely, no? So,
but that's what you can transition, because it's vanished, because they're all the same.
They're all the same, okay. But they're all the same.
So the definition of the Cobordism group is this. That's the definition. And that's a good definition. That's a good definition of a Cobordism group. Two things are equivalent if they are related by a domain wall like this.
Wait a moment. So I just understand. So they are all the same, okay, but then they also have to be the zero class in the sense that there has to be a bubble of nothing, in which the wall ends.
That's right.
Each other and also connected to nothing.
To nothing. Okay, good. No, then
exactly.
Okay.
Exactly. And so the Cobordism conjecture is that this group that we defined but we couldn't compute is actually vanishing. So everything is connected to each other and to the vacuum, as Irene just said. Okay, so that's the definition, and this is the conjecture. Okay, and the way you compute it is like this: is using this process of improvement in practice. Irene, you were saying something?
There's only one quantum gravity theory.
Okay, so
Yeah. I think she was trying to convey Baja's original motivation of a single quantum gravity theory out of this constraint. I mean, out of this proposal.
Actually,
right. So indeed, if this thing is true, right? If you can connect every quantum theory of gravity to any other, physically it follows there's just one, and that one is string theory, I guess, because we do know string, there's a concept of quantum theory of gravity, which is string theory.
Actually, it's very confusing why we are talking about quantum at all here. Because this is the question, is this equivalent class quantum G, QG1, QG2, and so on and so forth, is a quantum process or is a classical process? Because if it's a quantum process, it's coming with some probability. You have some coherent sums, you have new labels like the theta parameter, for instance, okay, a lot of things. Or is a classical thing?
So
I don't know why we are using quantum here. What is quantum here? There is nothing quantum.
It's a lot of singular spaces.
the topology changes.
But this definition of the equivalent class, new equivalent class that reduces the Cobordism group, I'm asking, is an equivalent class quantum or classical? What means quantum?
It's a definition. It's a definition.
Amplitude that there is some body that interpolates between this guy and this guy. Classical is not probability.
This is a definition. This is a definition which works both classically and quantum mechanically. Sometimes some of the cobordisms between objects are classical objects, and sometimes they involve things like topology chains, which are very much quantum mechanical. Right? So if, for instance, if I am doing classical gravity around one saddle, there's domain walls that if a domain wall between two quantum gravities involves topology chains, I wouldn't include it. Some other times where it just involves, let's say, moving across a conical transition, that's a classical thing I would include. The definition is general and covers both classical and quantum cases.
But then this domain wall and so on, I should understand it as a classical or a quantum process. If I understand it as a quantum process, immediately will create a new quantum number by the superposition of this QG1, QG2.
Right. So
this quantum number, because you are you don't like global quantum numbers, you will say to me that also these global quantum numbers will be zero.
No, I mean, so for instance, an example where this kind of thing becomes dynamical, right? Is when the vacuum that we're talking about, for instance, if we consider a domain wall between some vacuum and nothing, and the vacuum is non-supersymmetric, then, as you know, there's actually a quantum process, and you can compute the probability of nucleation of this bubble of nothing. So what can happen is that if you have some vacuum, right, some vacuum here, there can be a bubble that nucleates where there's nothing inside. Okay. And you can compute this nucleation probability, and it's, it goes like the area of the bubble, or 4G for Witten's case, and in more general cases has more complicated expressions. So you can certainly have dynamical processes associated to these guys, and in fact we believe that whenever supersymmetry is broken, these kind of things happen dynamically, although we don't have a proof. So yeah, it does happen dynamically when supersymmetry is unbroken. It's kind of like a marginal case where these things, they're actually, the nucleation probabilities, it becomes vanishing. And then in that case, I guess you could say still a classical process, because you can still consider configurations with the domain wall, but you gotta put them there by hand. But in the non-supersymmetric case, they actually nucleate. Absolutely.
Okay, guys, so we are way over time and diverging in the discussion. Miguel, do you have some final words, or?
No, I think that the best thing to do. I think that the best thing to do is that there's one application. So there's one application of Cobordism conjecture that I really want to mention because I think it's very exciting, but I will do that tomorrow. And so I think that we can wrap up at this point. And the basic point is that there is this idea which predicts the basic power. The nice thing of the Cobordism conjecture in practice is that it predicts new kinds of defects in string theory. And that's why it has gotten so much interest recently, why it's so powerful. That I'll finish. Thank you.
Okay, thank you. Good question.
So Miguel,
Yes.
in normal global symmetries, when you gauge them, you find like new global symmetries that appear.
Yeah.
Does something similar happen here?
Absolutely, absolutely. Yeah, the same thing happens. So for instance, look at the example of the heterotic, where you have the P1, okay, contracting class over 2, and I'm gonna introduce a B field that gauges it. But introducing this new B field that gauges it, it's gonna give me generalized global symmetries coming to, you know, the integrals of Wilson lines, right? Like B2 Wilson and generalized Wilson and tough lines, right? So I now need to introduce objects to break these symmetries. So this is the fundamental heterotic string, and this is the NS5 prime. So this is an example of the iterative process that I was describing. I start here, I do the first step where I gauge it, and then I get new global symmetries, which I need to gauge or break. Okay. In this case, it's interesting because this is a case where I cannot, interestingly, I cannot gauge, for instance, this symmetry, because gauging this symmetry would mean that the field strength of this thing is no longer gauge invariant because it's attached to something else. So I could not use in the Bianchi identity here. So this is a case where in the next step I need to break. Okay. But yeah, absolutely.
Great. I propose we wrap up and we go for lunch.
Yep.
You can have lunch too. Thank you. Thanks a lot.